What is going on YouTube? Just helping you out here. And in this video, I'll be doing Chapter 23, Problem 4, in the Fundamentals of Physics, 8th edition textbook by Walker, Halliday, and Resnick. Chapter 23 is all about Gauss Law, and in Problem 4, we have a cube, and we are told that there is an electric field on the top face and an electric field on the bottom face, and we are asked to determine the net charge contained within the cube. And so the first thing that I want to do is just draw a little diagram, and so we'll say this is our cube. We are just looking at it from one face, so it looks like a square, and we are going to have our electric field on the top face, just like that. That is negative 34 k hat newtons per coulomb, and we have the electric field on the bottom face, and that is 20 k hat newtons per coulomb. And then we have our vector normal to the area on the top face, and the bottom face. And that is the setup for this problem. And so we know that flux is equal to the charge enclosed over epsilon naught, where epsilon naught is our vacuum permittivity constant. And in this problem we are looking for the charge contained within the cube, which is this Q enclosed, so we can multiply both sides by epsilon naught to isolate our charge enclosed. So that's equal to flux times epsilon naught. And now we know epsilon naught, that's a universal constant, but we need to find our flux. And that is our total flux into the cube, which is the addition of our flux from the top and our flux from the bottom. So what we can do is say flux tot, our total flux, is equal to the flux in the top plus the flux into the bottom. And now for each of these individual fluxes, we know that that is equal to the integral of the electric field dotted with the differential area. Now in this case, both of our surfaces are planar, so this can be simplified, and that's going to be flux is equal to the electric field times the area. And again, our surfaces are the face of a cube, and we know that the face of a cube is a square, and the area of a square is equal to the side length squared. And so now we have the equations we need to calculate each of these individual fluxes. So I'm going to start with the flux on the top. That's going to be equal to the electric field on the top times the area of the top, and that is equal to negative 34 newtons per coulomb times our area, which is the length of the side squared, and we're told that that is 3 meters, so this is 3 meters squared. And one thing you just need to be aware of is this is a vector, so direction does matter, and in this case the vector normal to the area is pointed in the positive z direction, meaning that this quantity should be positive, and it is, so everything is good there. And if you plug this into your calculator, you will find that this is equal to negative 306 newtons times meters squared per coulomb. And now we can do something similar for the bottom face. So the flux into the bottom is equal to the electric field at the bottom times the area of the bottom, and that is equal to 20 newtons per coulomb times our area, which again is 3 meters squared. But in this case, the vector normal to our area is pointed in the negative z direction, so we need to introduce a negative right there. And if you plug that into your calculator, you will find that this is equal to negative 180 newtons times meters squared per coulomb. And so now we have both the values we need to find our total flux. So flux tot is equal to flux at the top, which is negative 306 newtons times meters squared per coulomb, and that is plus the flux at the bottom, which we found here to be negative 180 newton times meters squared per coulomb. And if you plug that into your calculator, you will find that this is equal to negative 486 newtons times meters squared per coulomb. And now we have our total flux that we can plug into this equation right here. So now we can find our net charge contained within the cube. So Q enclosed is equal to flux tot times epsilon naught, which is equal to negative 486 newtons times meters squared per coulomb times epsilon naught, which is 8.85 times 10 to the negative 12th coulombs squared per newton meter squared. And if you plug that into your calculator, you'll find that the charge enclosed is equal to negative 4.3 times 10 to the negative 9th coulombs. And if you want to write that in a little more compact fashion, you can say this is equal to negative 4.3 nanocoulombs. And that is the final answer to this problem. And so that's about it for this problem. If you found this video helpful, please drop a like, leave a comment if you have any questions or an idea for a future video, and lastly, please don't forget to subscribe and tell your friends about my channel so I can grow and help more of you guys out. I'm just helping you out. See you in the next video.